Alright guys, let's go ahead and get started. So we've been looking at some processes, things that are in contact with another. They're called thermal contact. Heat is this transfer of energy from one thing to another, or one system to another system. What did we do last time? We looked at counting the number of things in a system, called a mole. We looked at Avogadro's number, and what else? Zeroth law. That was that last time? I don't think. A little fuzzy on what we did quite exactly. It's all blending together a little bit. Today, we're going to look at how does an object change once you add so much energy. That's going to be this phase change of a state of matter. So if we continue to add more and more energy into an object, we just keep pouring energy into an object. We keep heating it up. We can't expect that object to remain how it is forever. Simply by the vibrations of that solid object, or maybe the flow of that fluid, it won't always continue at that rate. And so it will undergo what's called a phase change between a state of matter. And remember when we're talking about fluids and states of matter, there are about 4 that happen naturally. There's a 5th one that's man-made. But the 4 that happen naturally, I guess you could consider the 5th one also. It all has to deal with how much energy you put in or take out of the system. So, as a solid, you add energy to a solid, it will start melting. Just put both of those up there, sure. So, the easiest and best example for everyone to understand is ice. Ice is a solid. As soon as you add so much energy to ice, it will start to melt. It will start to change its structure, its complete state of matter, into something that it doesn't resemble anymore. It doesn't resemble its previous self. This is called the latent heat. We'll talk to in a minute. There's a sort of a threshold of something transferring from one to another. There's like this critical point for specific materials. For water, we based this whole temperature scale around it. We said 0 degrees Celsius is the freezing point of water. That's when it starts to change. It starts to act real weird, and now it's a solid all of a sudden. If we go colder than that, 100 degrees Celsius, that's when water starts to act weird again. That's when it's not held together. It's not bound by or more bound by gravity, being held in this container. It's free. It's this gas. So that's this temperature scale we've defined almost everything around. And what that's called is, so boiling, condensing. If we go from a gas and we take out some energy, say we reduce the temperature and we take out energy, we'll be going from this gas into a liquid. That's actually what happens in the mornings when it's really cold outside. It's cold enough that the air molecules, they start to slow down, they start to change their phase back into water. And so that's why we see water on all of the grass. In the winter it changes phase again, it turns into frost. That's frost on the grass. As well as when we have like a really cold drink, and we know things going from solid to liquid or melting or freezing. This sort of threshold that I was talking about That's called the latent heat needed for that specific material to change from one thing to another thing. Or I should say one state of matter to a different state of matter. So each material has its own different latent heat. And hopefully I can make this a bit more clear in a slide or two. So say you have water that is at 0 degrees Celsius. It doesn't all instantly just poof, transform immediately into ice. No, you can have water in the liquid form at 0 degrees Celsius. That's when it starts to, transform, it starts to change its phase at 0 degrees. So we can have liquid water at 0 degrees, but it takes a bit more energy leaving the liquid water in order for it to turn into the solid form of ice. When something is either melting or freezing, going from this solid to a liquid, or a liquid to a solid, that is called the latent heat of fusion. I think I have that picture. There we go. So that's a threshold. This ice that I have in this cup right here, it's starting to melt. That means it's sort of receiving enough energy to change its state of matter. Now, if things go from a liquid to a gas, or a gas back to a liquid, that's another different threshold that this material has to account for. That's called the latent heat of vaporization. And that's the main cause of, condensation or steam off of a, boiling pot of water. And hopefully this next one will make it, or pull it all together. So I was going to draw a diagram, but I found one. You guys had in your book already. I should also say, we may want to calculate, say, I know we've probably all had the specific heat lab so far, and we're looking at how energy transfers from one thing to another thing. Sure, we had like a hot piece of metal and some cold water, sure. But what if we had ice and we had a warm cup of water or something like that? So the ice cube, water, it needs to not only heat up, it needs to transform into liquid water. So it takes energy for it to transform. That's latent heat. So how can we figure out how much energy it needs? Well, that is just this. So this is actually a plus or minus. And the Q, that's always the exchange of energy, or how much energy is needed. M, that's the mass of whatever object we're looking at. And L, that's the latent heat. It could be vaporization or fusion. It could be either.
Professor?
Yeah.
Is the L value a constant for different types of substances?
Right, it's constant. So typically, I think in your book, you'll find many on the internet also, you just find a big table that says water's latent heat of fusion is this. Water's latent heat of vaporization is this. And it doesn't mean that they're the same values. They could be different values. In fact, for water, let me go to the next slide. For water, this is similar to that sort of little experiment I was suggesting. You have some ice, and you start to warm it up. So originally, it doesn't have that much energy in the ice. So it's very cold. All of the molecules are not moving. There's no like kinetic energy if things bumping together. Sure, not very much energy. But as soon as you bring it up to the temperature of 0 degrees, so you could have ice that's like negative 50 degrees Celsius. Sure. As soon as you bring liquid, or say, as soon as you bring water, ice, up to 0 degrees, you see right there that flat line? That means that the ice needs a little bit more energy in order to start transforming into water. Not all of the ice instantly becomes water right at 0 degrees. That's this little, like this. That's this little flat line right here. So I need to add a whole lot more energy right here in order for all of that ice to turn into water. Then once it is water, I could increase the temperature steadily up through here, sure. But then once I'm at 100 degrees Celsius, I have this sort of like threshold of like all of the water is, bubbling, sure, but it won't completely turn into steam until I add an incredible amount more energy, way, way, way over there. So this is what I mean by the latent heat of fusion or vaporization. They are not always the same value. In fact, it's common for them to be different values. For water, it's very significant. That's why it's, a chart in your book. So this sort of threshold needs to be overcome. I need to add more energy than that for all of that water to become steam.
All right.
Okay. All right, we'll do a little example problem. Let's see. So we start out with a certain amount of ice. We add it to a cooler that's holding some amount of water. So let's say 5 kilogram block of ice. It's at 0 degrees, so it's at that threshold limit. And it's thrown into a partially filled container that's holding 10 kilograms of water at 15 degrees Celsius. And I've added the latent heat of fusion of water is 3.33 times 10 to the 5th joules per kilogram. Now that is how much energy, or actually that's not the energy. I'm going to need to calculate the energy. So part of the question is find the final temperature of the two after you mix them. And we don't care about the container. We're just saying, warm water, cold water. That's all that's involved. And what was the mass of ice that's melted? So does all of the ice melt? Or maybe only a little bit of the ice melts? Like we have to figure out how much. Because if all of the ice melts, we have the answer right at the top. The total amount, 5 kilograms. We need to figure that out though. So let's see. So let's first figure out, I'm going to say, right here, how much energy does it take to melt all of the ice? So that's a valuable number. Maybe all of the ice melts. Take to melt all of the ice. All right. So I'm just going to say the energy it takes to melt. So Q, melt, sure. All right. And we're going to melt the mass of the ice. And so we're going to see how much it takes for all of the ice. And we need the latent heat. I'll just put that, sure. Okay. So what do we have? We have the total amount of ice, latent heat of fusion. So the latent heat of fusion is 3.33. Joules per kilogram. And we come up with an answer that is, I've done this before, 1.67 times 10 to the 6th joules. Okay.
Professor?
Yeah.
Why did you leave out the plus or minus?
The plus or minus, that's because I could include it, but I'm saying how much energy it needs to melt the ice. So I'm sort of let's see, how could I phrase this? How much energy do I need to provide into the energy? How much, maybe that's how you can think of it. I'm providing energy to melt the ice.
Okay, I understand that. Then what does the plus or minus mean then?
So it's similar, like providing or energy being taken away. So positive energy in, negative energy out. So it requires 1.67 times 10 to the 6th joules of energy that I have to put into the ice for it all to turn into water. Now water will be at 0 degrees Celsius. Okay.
It depends on what the question is asking, right?
For what exactly?
The plus or the minus.
Plus or minus, right? It's like, am I adding energy to this thing, or am I taking energy away from this thing? You can kind of think of it like that. Now, on that same topic, right? How much, what is going to be adding energy to the ice in this problem?
The surroundings?
The surroundings, and the ice will be in the water. So the water is providing the ice some energy. It's adding its own energy into the ice. So the water needs to provide that much energy in order for this block of ice to change its state of matter and itself turn into water. Okay. But that change of energy is going to change the temperature of water. As we've seen from the calorimetry examples. We take energy away from something, the temperature is going to decrease. So I could phrase it like, how much, phrase it like this. How much energy how much energy does it take, or no, how much energy can the water give before becoming 0 degrees Celsius? So that surrounding bowl of water, not a bowl, it's like an ice chest of water, is going to be transferring its energy into the ice to melt it. But it only has so much energy to give. We need to figure out how much energy can it give before that surrounding water is all the way at that threshold, 0 degrees Celsius. Because then it's going to, or I should say it's at risk of turning into ice itself. So let's see. Of water. This is, let's see, we had 10 kilograms. Specific heat of water was like 4190. Yeah. Joules per kilogram. Get those wrong. Okay. Degrees Celsius. And that sort of ice chest of water is going to be cooling down in temperature. It starts at 15, but it's going to reduce in temperature down to 0 degrees. Final.
So Professor,
Yeah.
What is our system in this problem? Is it the water or is it the ice?
In this problem, I'm going to like highlight the two systems in the next part. Right now, I'm just sort of thinking how much energy is each side. There is the hotter side, the liquid water, and then there is the solid, cold side, the ice. So there are two. I'm mixing them together. Yeah.
Why? Like, is there any way you could also do the Q equals ML fusion for this one as well? Because isn't for fusion going from melting or freezing? And this one
Right, yeah. I want to figure out, at this point, my main question is how much energy can the water give? So I don't know, say I have this thing of water right here. It's at some temperature, and I put some ice that's not the same mass, right? I don't know. In there, I'm not expecting the water to, this large tub of water to then turn into ice. So this sort of latent heat of fusion I'm doing right here, that's not something I'm necessarily wanting to use for looking at the energy in the water. Okay?
Is it because like for like latent heat of fusion, even if you're going to freezing, that's talking about the like everything freezing altogether, not just like the start of freezing? Is that why you don't use it?
Right, right. So maybe I can add a little on the board. So here we have like freezing. So there's this very fine like barrier, and things can be liquid still. Things can still be liquid and at 0 degrees. Right here. So I just want to figure out how much energy does it take to take something from 15 degrees Celsius all the way down to 0. I don't want to do that transfer. Whenever I do this transfer, that's when I use this latent heat equation I just gave. So whenever I'm transferring from one form to another, then I use that energy equation. And you see how much it takes to do that little jump. Either to a solid or, yeah.
So this would be like on the graph a couple of pages back where it's like the flat line of the phase change. That's the only time you use the latent fusion?
Right.
Okay.
Yes. Yeah, so this is the jump between the two. And it's that certain amount that you need, those flat lines on that previous graph, that's the amount you need to jump to the next phase. Or from solid to a liquid. You're jumping across that, state of matter. You figure out how much energy you need for it.
It's the linear line going this way. That's when we use the Q equals 1 type.
That's it. Yeah.
Okay. Also, I know you mentioned you're going to highlight the system and surroundings in the next part, but I can't help but ask, or just look at this and see that the ice. To me, the ice looks like it's a system because it's gaining the energy, while the water is going to be losing the energy.
Exactly. Yeah. So you think of it as two systems.
Okay.
I'm going to be combining them.
Okay.
Yes. So for this one, I'm saying how much for one of those systems, how much energy does it need for it all to change into to liquid? That's that first one up at the top. The next one down below it, make it blue. That's the other liquid system. That's saying how much energy does it have to offer for being a liquid at all? Because I could bring it all the way down to 0 degrees Celsius, and then it's no longer going to be a liquid anymore. And it will be at the temperature of the ice. So here we see the way that we have this sort of written. Final minus initial, this is going to be a negative. This is also related to if it's going to give or receive energy. Negative 6.29 times 10 to the 5th joules. Okay, so that's something very interesting. We see that up at the top, it needs a lot more energy. It's times 10 to the 6th. Down at below, the water can only offer 6.29 times 10 to the 5th. So that means, ultimately what that's meaning is the water cannot melt all of the ice. It does not have enough energy. It does not have a high enough temperature or a big enough mass to melt all of the ice that's thrown into the bucket. So how do we actually get around this? How do we figure out how much ice is going to be melting? First off, I can answer I can answer part A. You say that the system is going to go down to 0 degrees Celsius because the water is going to offer all of its energy. It's going to be reduced down to 0 degrees Celsius, and only some of that ice is going to melt. But then there'll be that ice and the water both at 0 degrees. As I said, they could both exist at that temperature. So put up here. Zero degrees Celsius. Okay. So how much mass of ice will be melted though? So let's look at, let's go like this. I'll write this again. So the water, I should have written it down on the board.
I have it written down. I believe
Okay.
it's 1.665 times 10 to the 6 joules to melt the ice.
All right, 1.6 to melt to melt all of the ice, right? Okay, but the water cannot offer that much energy. How much energy can the water offer? So the water, let me write this, water the water can only offer so much energy to melt. Nope. To melt just some of the ice. Okay, so the amount of energy that the water can offer is 6.29 times 10 to the 5th joules, and it's going to melt a certain amount of ice. That's where we can use this equation again. Latent heat of fusion of ice, or of water, sorry. Times 10 to the 5th joules per kilogram.
Do keep the Q negative?
So the reason that we are making this positive says we're looking at the ice system now. So like we were saying earlier, we could see it as two systems. The water's losing energy. That's why it was negative when we looked at it then. Now if we look at the ice system, it's gaining energy. Also, then our result would be a negative mass. You'd win some prizes if you found out a way to do that. So we have, let's go, so 1.89 kilograms. So what that means is there is 1.89 kilograms of ice was melted. So it's similar to this. Like you can wait as long as you want, but only a little bit of the ice will be melted. The water can only offer so much energy into heating up those ice cubes. Then the water itself and the ice cubes will both be at 0 degrees Celsius. Okay. Little tricky example here. We're going to get on to some demos here. Let's go to, energy transfer. All right. Look at that latent heat. We could take energy away from something. We could add energy to something else, heating it up, cooling it down. How can we do that? Well, there are a couple ways. There is conduction, there is convection, and there is radiation. Let's explain a little bit more about each of these. So, start out, conduction. For conduction, that's when we have something being heated, similar to that stove picture. In fact, I think I still have it. Let me. Something being heated, something has energy added to it, some fashion. Conduction, so thermal conduction is how easily heat and temperature will increase within materials that are touching. So for this little picture here, the heat of conduction is the time it takes for the handle to start to get warm. It's not, immediate. Some metals have a better thermal conduction than others. So I have, let's see, I have this piece of aluminum here, and it's wrapped with paper. And things you need to know that is if something is a very good conductor of heat, that means that as soon as one thing starts to heat up, on one side of the object, it will quickly move all the way through the object. That means it's a good conductor of heat. Think of it, moves the energy quickly. If something is a poor conductor of heat, that's also called an insulator. So in this case, we have an aluminum rod wrapped with a piece of paper. Aluminum, or I should say most metal, is a great conductor of heat. Paper, not so great. Paper and wood and other sorts of things. So it means the heat can't transfer through the paper that quickly. If I take a torch, find a spot. Over here. So we have the heat moving into the paper. The paper doesn't distribute the heat evenly. all throughout the whole surface. So it starts to just sit there and then burn. Whereas the metal is a great conductor. So I can grab this immediately. And it's not hot because the heat has transferred all the way through the metal and it's warm down here already. It's warm up here, it's warm down here already. So the heat moves quickly through metals. Aluminum is especially good. I've showed you guys this demo a couple days ago. Let's see if this works. So these guys, right? And I passed this around. You guys felt them. How did they feel? Which one felt colder? The metal. So that means the wood kind of felt warmer. And what temperatures are they exactly? Which one is colder than the other? In this case, they're both the same. That's the wood. Oop. Where's the glare? That's the metal. 73 about. Okay. So okay, yeah, 72, 72. They're the same. You guys felt it though. One of them felt colder. I didn't really explain why one felt colder than the other at the moment. That's because one of these is a great conductor of heat. The other is a very poor conductor of heat. The wood is considered an insulator. Heat doesn't move through it quickly. But metals, aluminum, and most other metals on the periodic table have the heat pass through them very easily. So I'm going to take an ice cube. Take an ice cube. Find two that aren't already gone. I'm going to put one on each. Which one is going to melt first? Which one felt warmer? The wood felt warmer. We've already seen they're the same temperature. As you can see, the aluminum block already has most of that ice cube melted. The wood one, it's barely starting to melt at all. It's still there. Why is this happening? Like I said, metals are good because they have this sort of, it's the atomic structure. They have this sort of free electron moving around that can move heat in and out all around the metal very easily. It's the chemical structure, the atomic structure of that material. Wood, being an insulator, its structure is just so that heat can't transfer that easily. We have the ice cube is just about gone on that one on the right. That was probably picking up the ice cube. But then the heat has transferred into the metal itself. Okay, very cool.
Professor, does that apply to, let's say, like you apply the same amount of heat to both the wooden and the aluminum block, and you, let's say you touch them, would the aluminum block feel a lot more hotter than the wood block?
Say I use the torch on both of them.
Correct. Yeah, and you apply the same amount of heat for the same amount of time.
Yeah. It's because the aluminum block, you think the heat spreads evenly throughout the entire surface. So over time, the heat will rise on the metal. If you do that to a block, a very small point what may be very hot, but the rest of the object will remain its original temperature. That's what I mean. The heat doesn't spread evenly on an insulator. Okay? All right, we have that and that we did. Okay. Next, we have that down. Convection. Just add all of these. Here we go. Convection is when there is movement. That creates this sort of flow, and that makes this heat move from one thing to another. I had the idea to bring a candle. When on the way to school, I was like, we're all wearing a mask. No one's going to be able to. I was going to see if you guys could smell the candle. Probably not. But convection is this sort of flow of things moving by the use of a substance that's already moving. So in the case of like your oven, right here, there's this convection setting that just turns on a fan. It spins around this air, creates this warming for your food to cook more evenly. Let's see, I have this all good. Let me do this one first. Here we have a chimney, something similar to your chimney in your house. Move this over here. Okay. Something similar to a chimney. We have I don't know how many people have chimneys anymore, but there's something inside of it called a flue. Looks like this. Just a piece of metal that's separating this tube. It's just a big empty tube. And it's shifted over to one side, so the tube is split up into two halves. And that makes this easier for the heat produced by this flame to move, to circulate. So we have this over. So the heat, this candle, it can't sort of spread it out anywhere. I've blocked it off, sure. The heat is moving up one side, and fresh air is able to move down the other side. You didn't have this. You just had that sort of big opening, and this large thing being, large tube blocking it. Then the heat sort of comes up and slows down. It starts blocking all of the oxygen. Makes the candle go out. Makes the flame die out because there's no more oxygen down here. That's a small example of convection. I think it's a little iffy because not everyone has a fireplace anymore. Right here, we have a tube of water. Let's see.
here.
And I'm going to add some heat to it. Okay. Now, this has been sitting here for a while. The water is stable. It's all probably the same temperature because I did this a while ago. I'm going to put some food coloring so you can see how the water is moving. Just one, maybe two. Sure. It kind of just sits there, spreads out evenly. As soon as I add some heat, there will be this convection happening. Heat often makes things more energetic. It makes things sort of expand, move faster. So when I heat something, it will often make it rise. You know, it says hot air rises. This is the case for liquids as well. So we have this sort of natural convection happening in like lakes, other even like geological sort of areas, tectonic plates have this convection, this sort of rolling effect of being heated up and expanding and rising and then cooling down and then coming back around. So just by heating this up, I'm creating this movement inside of this tube. And now it's pretty much all blue. You can't really see anymore. Yeah. Okay. Yeah. That's right there. Okay.
Professor?
Yes.
Does air have a convection property?
It does. Yeah. You heat air up, it rises, it becomes less dense, it expands. But then as soon as you get really far up, it's not warm anymore and it cools down. And when air cools down, it comes back together. And you have enough, maybe, I don't know, water in that sort of air coming together, it creates clouds. And clouds always form at a specific height. You've ever seen a long drive, flat road, you see clouds are almost all at the same height. Or some of them. There are different types of clouds. It's because there's this sort of temperature gradient. Things get colder as they get higher up. But then also differences with pressure. So that's why we might see clouds always at a specific area. They're never really clouds passing on the ground. So it's a different pressure, it's different temperature, things like that. That's that. Okay. Next, we have radiation. Radiation may sound scary, but it's not. Okay. So radiation is something that is almost, let me see how to phrase this. It's the transfer of energy through the electromagnetic spectrum. So things that produce electromagnetic waves can produce radiation and heat something up from a distance. You ever wondered why the sun is able to heat up Earth by being so far away? It's not even touching it. It's not even convection. Things moving around in space don't bring heat in. It's this direct electromagnetic waves that come directly from the sun onto the Earth's atmosphere. This picture right here on the left, that is a radiator. That is, sometimes you'd have those in a building, run hot water through some pipes, and just by having something warm around, this heat, this sort of warmth, is emitted off of this thing. You guys ever been just near something hot? You could feel it without being near it, right? That's radiation. That's this sort of thermal radiation that's being produced. I should also say that this is just something that everything on Earth produces. So you shouldn't be afraid of this. This is just heat. This is just the object's temperature. This right here is looking at infrared light. So let me show you the spectrum right here. So for everyday life, we see things in color. We see things with light. Everything we know of that we can see is within this rainbow right here. But that's only a small, tiny little sliver of things that are on this electromagnetic spectrum. So say we go more to the left. We go from yellow, green, blue, violet. We go just a little bit more, we have ultraviolet. That's something where the waves start to become a little bit closer together. That's being produced by the sun, sure. That's something that might give you a sunburn. You go a little bit more, you make the waves compact a little bit more. You get something that's very energetic. It can go straight through your skin, show you pictures of your bones, maybe. We go even farther, that's something we only experience in like outer space, we can measure. If we go past red on the right, we get to things that are infrared. So if we go through this visible spectrum, past red, we get to infrared. That's just an object's heat. That's its temperature. Everything, you and me, we emit this infrared light that is coming off of us. Those were those sort of like orange and yellow pictures I keep showing you. So that's looking at this infrared light. We keep going past that. We look at microwaves. Something that is able to add energy from a distance enough to shake water molecules and heat them up. We keep going, we get into radio. All of these things are the same type of waves. They're the same type of thing. While we're on this picture, before we leave this picture, I heard a story of like in the 40s when they were doing military testing. They were testing out radio, like shortwave radio waves and radio emitters, a bunch of different weapons and things they're trying to test. And the soldier, the person in charge of this test they were doing, they got like the huge gun, kind of like a big thing shooting out radio waves. And this guy's standing back off to the side, and he notices that he had a chocolate bar was in his pocket, in like his coat pocket, and he just put it in there. It was already like cold, and already it started to melt. And they figured out he was standing next to it, and the radio wave was not functioning correctly. It was sending out microwaves. So he was slowly being heated up by standing next to that radio wave emitter. What else? Right. So I want to do my last demo. I have this. This is one way to show radiation. We have this incandescent lights. We might have them, we might not. They're really old-fashioned light bulbs. we have a new light. This is LED. So, light emitting diode. If I shine this on this little meter here, nothing happens. It's producing just light. But the reason we've changed to these, and these lights up ahead, in new TVs nowadays, why everything is LED now is because it's more efficient. It's producing just light. That's all I need. We don't want what these old-fashioned lights are doing. It's producing light and infrared heat. I can put my hand in it. I can feel some warmth, sure. So I'm heating up one side of these dials, making this spin. That is a small demonstration of radiation. Let me do one more, then we can call it for today. Let me go get it. And
Technically, heat is a good thing, but it can show us also. That's a really good thing that you said that. Philosophy, one of our types of philosophy, everything in the world. I agree with that.
okay, so on one of these dishes, I have a sort of a clamp, and it's holding a match. Behind it is a dish that's perfectly mirrored and polished. It's made of metal, and it will reflect anything that's pointed at it. Over here, I'm not going to point at you guys, I have a light. I'll show you. So I have a light that is incandescent. It produces some heat. I'm going to just direct it at that thing over there. You can see that I'm going to transfer this heat, this energy, by means of radiation. Sort of similar to this sort of picture we have up here. See? See how far away we can get.
What's
Already.
Professor, is that how cell phone towers work in satellites? They send the heat through waves, and then that energy is used to produce signals?
Not heat. They use their own specific type of wave. It's a radio wave. Things like that. It's the same idea. I'm producing this wave over here, and it's just moving across space. Something over here is catching all of that energy. That's the same idea as what I just did right now.
Oh, but a wave is energy, right?
A wave is a sort of a movement of energy, yes.
Okay.
All right, and that's pretty much all I got for today. No class Thursday. Let's see. Make sure you work on your extra credit and the homework that's due a while from now. Next Friday. Yes. I did not. What would I have them out with? We are done with quizzes. Our exam is 2 weeks from now.
And it was literally off. Yeah. So that's why I'm asking like Yeah.
Need anything?
No.
Yeah, we saw it. I've got some questions.
Oh.
It's not like,
Alright.
Those are later for me.
So I just wanted to see if there was like somewhere I could find one that like matches a question report. Because it was like, I don't remember, I think it's question 9, but it was like, it was like one decimal off and I kept getting the wrong answer. So are you gonna like, for the exam, will you provide?
I'll give you, right, I wouldn't leave you
Okay.
without a chart or a table or something that I
Okay.
can use from.
Correct, thank you.
So, Professor, it's interesting that this energy that we can create, like, for example, nuclear energy, right? Is that basically just heat being released?
Nuclear energy is.
Or like, let's say like you, nuclear bomb, for example.
Sure.
And when it's dropped, is that just heat being